Hello, Raters. Let's go through some molar conversion problems. In our first example, we have this question: how many molecules of sugar are in a mole? And they give us the formula of sugar right here, and I can tell that this particle right here is itself a molecule. I know that it's not an atom because I see three different types of atoms here. I see carbon atoms, hydrogen atoms, and oxygen atoms. So they're asking me how many molecules are in a mole of this particular molecule. By definition, when we were talking about what a mole is, 1 mole of anything equals 6.02 times 10 to the 23rd of that thing, whatever type of particle it is. Because this is a molecule, our answer here is the number of molecules is this number right here. And that's it. There really wasn't any math involved in that question. However, if you were asked to show math for that problem, we could use our steps to do conversions, which anytime you get stuck on any of the dimensional analysis problems, always go back to this reference in your journal. That's what it's there for. Right, so to do conversions, we're going to need to draw a grid just like this. Put what is given in the upper left corner with the unit, copy the unit diagonally to the lower right corner, and then put what you're trying to go to in the upper right hand corner. All right, so I have that set up right here, and we don't always have a direct relationship between the unit that they gave us and the unit we're trying to go to, but in this case, there is a direct relationship between moles and molecules. 1 mole of this particular molecule is Avogadro's number of molecules. And your units would cancel out here. Your answer would just be this then. And that's it. So we've talked about using conversion factors. We've not specifically defined what it is, but this is its definition. A conversion factor is or are equivalent values having different units that when set up as a fraction equal 1. So they are equivalent values. And that's part of our number 5 step for doing dimensional analysis is when you have your units, you find an equivalent numerical relationship. For example, this right here, 1 dozen equals 12. Notice I don't have the type of thing that it is. It's just 1 dozen of anything equals 12 of that thing. This is an equivalent numerical relationship. It just has different types of units, right? If I have 1 dozen eggs, then it would be 12 eggs. If I have 1 dozen cats, it would be 12 cats. Okay, so because they are numerically equivalent, I could put these two values in a fraction with a numerator and a denominator. Because they are equivalent values, it's the same thing as if I wrote 12 eggs over 12 eggs. It would be as if I'm writing the same thing over itself, and anything divided by itself equals 1. So conversion factors can look like this. When set up as a fraction, they can look like this, or we could even write this exact same conversion factor here. Instead of having the 1 dozen eggs on top, I can have the 1 dozen on the bottom. I could write it as 12 eggs over 1 dozen. And the only reason why I would flip it like that is depending on what unit I needed in my answer. The unit that I want to get to is always in the upper right-hand corner, so that's what would tell you what goes in the numerator, right? So we have other examples here. So we've got, for example, 1 hour equals 60 minutes. In that example, you could use this conversion factor right here, and you could set it up this way with 1 hour in the numerator, minutes in the denominator, or If you needed minutes for the unit in your answer, then that would go on top and hours would go on the bottom. Because they are equivalent values, it's the same thing as writing, say, 60 minutes divided by 60 minutes. So it would equal 1. Again, we would use this to change the units, even though what we end up with is going to be the same value. So, for example, if I wanted to know how many, let's say, I wanted to know how many minutes are in 3 hours, or how many minutes long are 3 hours. Okay, let's say that's my question. I'm given the value of 3 hours. I'm going to multiply that by a conversion factor with hours on the bottom right. And I do have a relationship between hours and minutes, so I can use just one step. And setting it up this way, I can very easily make it look like those little train tracks that we set up, right? Everything in the numerator multiplied and then divided by whatever's in the denominator. 1 hour is 60 minutes. So when we multiply the numerator across the top, we have 3 times 60. That's 180. Hours cancels. So that's how many minutes. It's the exact same value that we started with, 3 hours, but it's translated into the unit of minutes. Why do we care about this in chemistry? Well, anytime we have foods that need to have labels for how many calories are in them, thermochemistry is involved. That amount of energy that goes on your food labels was determined chemically. If we have a doctor or a nurse who needs to figure out how much medicine a child needs versus a full-grown adult of that same medicine, dimensional analysis is how we find that out. And really, anytime we create any new chemical, any new product, there's dimensional analysis involved. Let's look at the setup of a dimensional analysis problem. So here is some multiple choices, and I can tell just by the starting amounts that they give me that I'm going to be converting grams into something else. And so my task here now is to make sure that we have followed our steps for dimensional analysis. So I've added here the chart that we've been using, and it says to draw a dimensional analysis grid. And this does look a little bit different than what we've been doing in class, but remember that this is a nice, easy way to put together all of these multiple conversion factors. And so we're still following the same format with the units, and we're going to still use how those units cancel out and put equivalent numerical relationships within the structures here. So let's see how we're doing. So we're starting off with 27.76 grams of lithium. And if I look on the periodic table for lithium's, it's right over here. And I see that there is a mass on the periodic table of 6.94. This mass on the periodic table is always what we're calling the molar mass, because that's not a mass for one lithium atom. It is for a mole of lithium atoms. Atoms are too small for us to see by themselves, so we have to have a huge amount of them, a mole of them, in fact, to be able to measure a good amount. So I know that I should be seeing 6.941 grams somewhere in here in order to be able to cancel out the sample that they've given me. And look, it's in sample 1. It's in the first answer choice. Oh, it is not at the bottom of the second answer choice, so B is going to be canceled. That's not going to be an answer choice for us. So the next one that we have is C. We have grams of lithium, and on the bottom right, that's not grams of lithium, so that does not work. Grams of lithium, look diagonally. Grams of lithium, yes, it is there, so that will work for us. I want to go ahead and take out these answer choices that we know cannot be correct. so we can just focus on the ones that could be correct. And I'm going to do something else here. Because we are used to seeing these in a certain format, let's go ahead and make our answer choices in that same format. So any number over itself, like our given amount here, is that number over 1, right? If we want to make this look like our table that we've been doing, just make this one big long fraction. That's all we've been doing, is making one big long fraction. And our conversion factors are things that we're multiplying by, because that's what factoring is, right? Multiplying. So wherever that multiplication sign is, we are putting a line, because that's separating our different conversion factors. So we have this right here. There we go. And if it bothers you that this space under here is blank, go ahead and put a 1 underneath it. It doesn't change the value at all. All right, so we said that the first two setups are good, right? We've got our starting unit copied diagonally. We're going to another unit. We're going to a unit of moles. Now we have to look at the very last conversion factor and see if that is properly set up. So looking at our unit here that's left, because if we were to stop our calculation just here with that one step, grams of lithium would cancel out. Let me go back to that. Grams of lithium would cancel out, and we would be left with a value of moles. But they have another conversion factor, so now we have to see if it's set up correctly. If I have moles of lithium so far, I should see moles of lithium at the bottom to be able to cancel, but that's not. That's not moles, that's atoms. So I cannot use that to cancel out my unit. I can use this one to cancel out the unit, since the exact same unit is copied down diagonally. So I know that this first one cannot be the answer. My answer choice then has to be this one. That is the one that is set up correctly for dimensional analysis. All right, so let's do some for real chemistry problems here. If you have 5 grams of lithium fluoride, how many molecules do you have? So they're giving me grams. They want me to go to molecules. I think this is going to have to be a multi-step problem, but that's okay because we have our conversions notes to help us, and we can do this. So step 1, draw a dimensional analysis grid. Check. Put what is given in the upper left corner with the unit. I'm given 5 grams of LiF. 5 grams lithium fluoride. Check. Copy the unit diagonally to the lower right corner. My unit is grams of LiF, grams of lithium fluoride. Check. Put the label of what you're converting to in the upper right-hand corner. Now here's where I need to put on the brakes. They're asking me for molecules, but I do not know of a relationship that goes directly between grams and molecules. The only relationship I know of that will let me convert to grams, is if I go to moles. That's where I'm going to have to go. And anytime I see moles and grams, I know that I'm going to have to go to the periodic table. So let's look. We have lithium and fluorine. They gave me the formula. I have one of each. So let's add that up. Let's see. Lithium is 6.94. Fluorine is 18.998. Ooh. So let's do lithium. There's 1 at 6.94. Fluorine, we always go to the hundredths place, but look at what's at the hundredths place. It's a 9. And if I'm going to round at that hundredths place, I have to look at the number right behind it. So that 8 actually makes that 9 into a 10, which makes this a 10, which makes that 19. So I have 1 fluorine at 19 grams. Adding those two masses together, I get 25.94 grams per mole, because it takes a mole of these teeny tiny particles to be able to weigh them. So it's 25.94 grams per mole. So now I can come back and put that in here. 25.94 grams per mole. 25.94 grams per 1 mole. All right, but I'm not there yet. I can't stop because that's not molecules. So what I have to do now, if I were to stop here, my numerator and my denominator would allow me to cancel out my unit of grams, but I need to cancel out moles. So I need to keep going. Let's copy diagonally. So I'm just gonna end up repeating that step where I copy my unit diagonally. So moles are here. And now I can put molecules up here. Can I move you? No, I can't. Let me move you over this way. Molecules. There we go. And let's see, I still need to put in a number, right? Let's see. So I finally did number 4. I was able to put the label that I was converting to in the upper left-hand corner, so I can check that off. Fill in an equivalent numerical relationship. Well, we kind of did that here, where we were putting an equivalent relationship between grams and moles. We need another equivalent relationship between moles and molecules, which is what this is. It's a molecule. I know that 1 mole of anything is 6.02, I'm going to have to squeeze this in, times 10 to the 23rd of that thing. And LIF is a molecule, so I know that I can stop my calculations here. I don't need to go to atoms because they did not ask for atoms anywhere in the problem. So this is all I have to do for the setup. Now, multiply everything above the line and divide by everything below the line. So in my calculator, I'm going to put 5. You don't have to put times 1, but you can put 5 times 6.02 times 10 to the 23rd. I would put those in parentheses and then divide 25.94. And you really don't have to do it times 1 because it's the same thing. And then, once you've done that, you should get 1.16 times 10 to the 23rd molecules. Or if you're going to write it the way the calculator likes to speak to you, remember, if you speak the calculator's language, you'll understand what it's trying to tell you. It'll look like that. And still, molecules as the answer. Okay, let's do another one. So this problem asks, which conversion factor should be used to solve the following? How many moles in 28 grams of CO2? That's carbon dioxide. So they're asking for a conversion factor. So that could either look as an actual fraction, or it could look as one value being equal to another value. Okay, so let me try and set this up then. I'm going to start with 28 grams of CO2. I can start with my dimensional analysis grid if I want to, just to make sure I'm consistent in my problems. But if I do that, I know that what I'm starting with is 28 grams of CO2. That means if I'm going to, done, copy the unit diagonally. So the next thing I should do is I should have grams of CO2 copied diagonally. And then what I'm converting to, now I do know a way to find a relationship between grams and moles. That's my periodic table. So I can do that. So then what I need to do is I need to go find that equivalent numerical relationship. That's my conversion factor right here. So I know that anytime I take it from the periodic table, it's going to be 1 mole to however many grams it says. So let's go find out how many grams are there. So I've got CO2. I'm interested then in carbon. And carbon is 12.01. Then there's oxygen, 15.999, which if I round to the hundredths place, that 9's going to kick that up to 10, 10, 16. So when I find my molar mass of that molecule, again it was CO2, that means I have 1 carbon at 12.01 grams per mole. I have 2 oxygens at 16 grams per mole, which is actually 32. Add together the 12.01 and 32.00, and I get my molar mass to be 44.01 grams per mole of molecules. So that's what I'm going to use. This is essentially my conversion factor right here. Now, if they asked me to put that in the right format for my calculation, I would need to put the 44.01 in the denominator, and then the 1 mole, and that would set up my calculation. So we could either go with this as our proper conversion factor, or if they were asking us what these values were, you could also write that out in this way. 1 mole equals 44.01 grams of CO2. So that's it. Those are the 2 ways that we could have written that conversion factor. So if you can get through setting up these problems and you're still having trouble, then we need to look at how you're putting these numbers into the calculator. And that needs to be done one-on-one, so you can come in for tutoring for those. Good luck.